This is a signal transmission tower. If you turn on your TV at home, it picks up the tower's signal and lets you watch a live football match in real time. But if you're in Europe and want to watch a World Cup game being played in North America, you would have to build hundreds of relay towers across the Atlantic Ocean to pass the signal along hop by hop. That would be absurdly expensive. And worse, every relay degrades the signal. By the time it reached the other shore, it would have decayed into noise. So you come up with another idea, beam the signal up to an artificial satellite, and let that satellite relay it back down to the ground. Because there's no mountain or curvature of the Earth blocking the line of sight between the ground antenna and the satellite, you only need one hop. That saves money and delivers excellent signal quality. However, the Earth rotates. To maintain uninterrupted transmission, the satellite must move in sync with the planet. That is, complete one orbit every 24 hours. But since it has to work continuously for a very long time, relying on conventional chemical fuel for steady propulsion is unrealistic. You need a new way to keep it moving. You observe that the satellite has an orbital velocity, and it also feels Earth's gravity. That gravitational pull can provide exactly the centripetal force needed for its orbit, much like swinging a ball on a string. According to the centripetal force formula, the centripetal force equals the mass of the object times the square of its angular velocity times the radius of the circular motion. The ball and the satellite must complete one orbit every 24 hours, so its angular velocity must match Earth's rotational angular velocity. With mass and angular velocity fixed, a longer string means the ball needs more centripetal force, and it also moves faster in linear speed. The length of the string is the satellite's orbital radius. The centripetal force comes from Earth's gravity. You know that gravity weakens with distance, but the required centripetal force increases with radius. If gravity is stronger than the required centripetal force, the satellite will gradually spiral down toward Earth. If gravity is weaker, the satellite will drift away into space. Therefore, for a fixed angular velocity, there is only one altitude at which gravity exactly equals the required centripetal force. Calculate that orbital radius, adjust the satellite's speed during launch, and in theory, you achieve synchronous motion with Earth. We know the geocentric gravitational constant, denoted by mu, is 3.986 times 10 to the 14th power, with units of cubic meters per second squared. Earth's rotational angular velocity, mega, equals 2 pi divided by the orbital period. The period is 24 hours, which is 86,400 seconds. That gives omega approximately 7.27 times 10 to the negative 5th radians per second, roughly 15 degrees per hour. Now you need to compute the satellite's orbital radius. Start with the centripetal force formula, then bring in Newton's law of universal gravitation. Gravitational force equals the geocentric gravitational constant times the mass, divided by the square of the radius. Set gravity equal to the required centripetal force, then the mass cancels out on both sides, so the satellite's mass doesn't matter. Multiply both sides by the square of the radius, rearrange, and you get the cube of the radius equals the geocentric gravitational constant divided by the square of omega. Now plug in the numbers. A simple calculation gives the orbital radius as approximately 42,200 kilometers. Earth's radius is about 6,370 kilometers. So the altitude above the surface is 42,200 minus 6,370, which equals 5,830 kilometers. That is the height at which Earth's gravity keeps the satellite circling once every 24 hours. Strictly speaking, 24 hours is a solar day. Earth also orbits the Sun, so it rotates an extra degree per day relative to the stars. The precise period is the sidereal day, 23 hours 56 minutes and 4 seconds, but the difference is tiny. Next, compute the satellite's linear speed. Linear speed equals angular velocity times radius. A quick calculation yields approximately 3.07 kilometers per second. And there you have your final answer. Launch a satellite into orbit at an altitude of 36,000 kilometers with a speed of Mach 7 kilometers per second, and it will stay perfectly synchronized with Earth. Place 3 such satellites equally spaced in this orbit, and you can cover virtually the entire planet, except the polar regions with continuous signals. Congratulations, you've just invented the geostationary satellite. But to keep it working reliably, there are 2 hard rules. First, the satellite's orbit must lie exactly above the equator. If the orbital plane is tilted relative to the equatorial plane, the satellite will still orbit stably, but it will drift north and south every day, unable to cover the same fixed region consistently. That would ruin the stability of continuous signal transmission. Second, to prevent interference between satellites in this crowded orbit, the International Telecommunication Union mandates that adjacent geostationary satellites maintain a minimum angular separation, typically about 1 to 3 degrees. Every position in this orbit is extremely valuable and must be allocated by the ITU. Countries without launch capability can hire others to launch on their behalf, paying back the cost with cash or by leasing communication services. That is the geostationary satellite. Today, the vast majority of transoceanic TV broadcasts, international phone calls, and maritime communications rely on this very principle. They hang above the equator, linking every corner of the globe, bringing live sports across continents, keeping far, voyaging ships connected to shore, and allowing families thousands of miles apart to hear, in the same instant, the love and longing that transcends every time zone.